Imagine an incredibly exclusive underground club. You walk up to the door, and the VIP bouncer standing there is, well, he's imposing, but he operates under a really bizarre set of rules.
Yeah, bizarre is probably the best word for it.
Right. Because he doesn't check your pockets. He doesn't, scan your backpack or care at all about what you might be smuggling inside.
Which is kind of the exact opposite of what you want a bouncer to do.
Exactly. This bouncer only cares about two things. Are you on the approved guest list? And can you perform the club's highly complex secret handshake without a single mistake?
Right, and if you mess up even a little bit...
You are tossed out into the alley immediately. But if you pass both of those, he unhooks the velvet rope, lets you inside, and turns a totally blind eye to whatever you do for the rest of the night.
It sounds like an absolutely terrible way to run security, honestly. Especially if you're worried about what people are actually bringing into the venue.
It really does. But in the architecture of a network, that specific approach is actually a foundational piece of engineering. We're going to get into exactly why you would ever want a bouncer that ignores the cargo in just a moment.
It's a pretty fascinating trade-off once you dig into it.
It is. But first, for our ever-curious listener out there, you're tuned into the WeCyberYou Unlocked podcast. Please take a second to follow the channel wherever you're listening, and make sure you visit WeCyberYou.com for more deep dives into the hidden mechanics of cybersecurity.
Yeah, there's a massive library of content over there designed to break down, how the digital world is really built.
Totally. So for this deep dive, our source material is a technical breakdown of a very specific piece of network architecture. It's known as a circuit-level gateway. And when you normally think of a firewall, you picture this massive, impenetrable wall scrutinizing every single bit of data trying to cross the border.
Right, checking every passport and opening every suitcase.
Exactly. But this technology completely throws that assumption out the window.
It really does. The sources paint a pretty wild picture of a system that operates primarily at layer 5 of the OSI model. And for anyone who might need a quick refresher, the OSI model is basically this conceptual framework that breaks down how network communication works into 7 distinct layers.
Right, so down at layer 1, you have the physical stuff like the literal copper cables and fiber optics.
Yeah, the actual hardware. And then up at layer 7, you have the application layer. So that's the web browser or the email client you're actually interacting with. Layer 5 sits right in the middle. It's the session layer.
So we aren't down in the basement dealing with raw voltage. But we aren't up in the penthouse looking at actual web pages either. We're in this, this middle management zone.
Middle management is a great way to put it. That zone is dedicated entirely to controlling and validating network connections. So instead of inspecting the actual data like the payload of the packets, a circuit-level gateway focuses its entire existence on managing what we call circuits.
And reading through the documentation, that word circuit can be a bit confusing. I mean, it makes you think of a physical electrical circuit on a green motherboard or something.
Yeah, but we're talking about something entirely virtual here.
Right. So walk us through what a circuit actually is in this context.
Well, logically speaking, a circuit in this context is a virtual communication path between two endpoints. Think of a client, like your personal laptop, and a destination, like a remote server hosting a database.
Okay, so there isn't a dedicated physical wire running from my desk to that specific server.
Exactly. Instead, when a connection is established, the gateway creates a logical tunnel over the public network. It's essentially an agreed-upon, sustained conversation between those two machines.
It's an active, recognized relationship for a set period of time, then. And the gateway manages the life cycle of that relationship.
It does, and the source material outlines this life cycle in 5 very distinct, highly rigid steps. Step 1 is the initiation.
This is the secret handshake from the club analogy.
Spot on. The technical term for that handshake, assuming we're talking about TCP traffic, is the three-way TCP handshake. When your browser wants to talk to a secure website, it doesn't just start shouting data at it.
That would be chaos.
Total chaos. It sends a SYN, or synchronized packet. That's your laptop reaching out and saying, hello, I'd like to establish a connection, and here's my starting sequence number.
Okay, and the server then has to respond to prove it's actually listening, which is the SYN ACK packet, right? Like, yeah. I acknowledge your request, and I'm synchronizing my own sequence numbers with yours.
Yep, and then your machine sends a final ACK, or acknowledgement. Got it? We're officially in sync.
So the gateway is watching this entire exchange happen.
Right. It's monitoring every step. Which brings us to step 2, the validation phase. The circuit-level gateway intercepts this request and evaluates it against a really strict set of administrative rules.
Like checking the VIP list.
Exactly. It checks the source IP address. Are you coming from a known trusted subnet? It checks the destination port. Are you trying to access a service we actually allow, like standard web traffic on port 443?
And most importantly, I'm guessing it verifies that the TCP handshake happened in the correct, mathematically sound order.
Absolutely. If a machine just tries to skip the pleasantries and start sending an ACK packet without ever saying hello first, the gateway sees that the sequence is out of order and drops the connection instantly.
Wow, so it's not messing around. If you botch the handshake, you're out.
It ruthlessly enforces the protocol. Now, if the connection passes that rigorous validation, we move to step 3, which is establishment. The firewall officially creates a virtual circuit entry in its internal memory.
This is often called a state table in the docs, right?
Yeah, state table. It logs the source IP and port, the destination IP and port, the protocol being used, the exact timestamp the connection started, and the timeout parameters.
Right, timeout parameters being the rule for how long this connection is allowed to sit idle before the bouncer steps in and says, hey, you're not doing anything, time to leave.
Which is crucial for preserving network memory and bandwidth. You can't just leave dead connections open forever. But once that entry is written into the state table, the logical tunnel is fully formed. The relationship is approved.
Okay, and this brings us to step 4, which is forwarding. And I have to say, this is the part of the documentation that really stopped me in my tracks.
Oh, I bet I know why.
Yeah.
Yeah.
So the tunnel is built, the bouncer has let you in. During this forwarding phase, the gateway simply takes packets from the source and passes them to the destination. It does not inspect the packet contents at all.
Nope, not even a little bit.
It builds this heavily fortified, heavily scrutinized tunnel, checks your IDs, verifies the complex math of your handshake, and then completely turns a blind eye to the actual conversation happening inside the tunnel. I mean, why design a security checkpoint that ignores the cargo?
It's the natural reaction to have when you first study this architecture, for sure. Why build a checkpoint if you refuse to look in the trunk of the vehicle, right?
Yeah, it feels entirely counterintuitive.
Well, to understand the logic, you have to look at the primary constraint of early networking, which honestly is still a constraint today. And that is the massive computing cost of deep packet inspection. By deliberately skipping the payload inspection, a circuit-level gateway operates with blazing speed and ultra-low latency.
Ah, okay, so it is a deliberate trade-off. You're trading microscopic scrutiny for absolute velocity. Let's quantify that for you listening, because the sources gave a really great breakdown of how this compares to other types of firewalls.
Yeah, context really helps here. If we look at Layer 3 and Layer 4 packet filtering firewalls, they just inspect individual isolated packets. They look at the source and destination IP.
Which is similar to a postal worker sorting mail by looking only at the zip code on the outside of an envelope, right?
Yeah. That's a great analogy. They can process millions of envelopes a second because the task is incredibly simple. But they have zero concept of a broader conversation.
So if you send them 50 envelopes in a row, they treat each one as a brand new, totally isolated event.
Exactly. Then you jump all the way up to Layer 7, the application firewalls. These are the invasive customs agents. They are taking the envelopes, steaming them open, pulling out the letters, reading every single word to check for malicious intent.
Checking the spelling against a database of known threats.
Right. Putting the label back, resealing the envelope, and sending it on its way.
Which is obviously the most secure method.
It is, but it is also incredibly slow and resource-intensive. Imagine the processing power required to do that for 100,000 packets per second. It introduces significant latency to the network.
Okay, so sitting perfectly between the dumb postal worker and the invasive customs agent is our Layer 5 circuit-level gateway. It understands the session. It knows you're sending a sequence of 50 letters, but it flat out refuses to open the envelopes.
You got it. It manages the flow, not the content.
To bring in another analogy here, it's like an opaque, high-speed pneumatic mail tube system. You know, like the ones at bank drive-thrus.
Oh, yeah, the plastic tubes.
Right. So the gateway's job is just to ensure that the pneumatic tube connects the client station to the teller station safely and securely. It verifies you are allowed to send a tube. But once that tube is zooming through the pipes, the system does not pause the tube mid-flight to look through the plastic and read the deposit slips inside.
Right. It simply ensures the delivery mechanism is unbroken. And we also have to discuss step 5 of the life cycle here, which is termination. The gateway doesn't just leave these tubes open forever.
That would be a huge security risk.
Yeah, and a waste of resources. It actively monitors the traffic flowing back and forth for specific control signals, specifically FIN meaning finished or RST meaning reset packets. When a computer is done downloading a file or loading a page, it sends a FIN packet to formally close the conversation.
It's the equivalent of saying goodbye before hanging up the phone.
Exactly. When the gateway sees that goodbye, or if the timeout parameter we mentioned earlier is reached, it tears down the virtual circuit. It deletes the entry from its state table and releases those network resources.
The bouncer kicks you out, and you have to do the secret handshake all over again if you want to come back.
Yep. Managing that cleanup process is just as important as the initiation. Otherwise, the firewall would just run out of memory trying to keep millions of dead sessions open.
Makes sense. But beyond just the speed, the documentation points out another massive advantage to this setup, which is network abstraction.
Network abstraction is where this technology really shines. In a lot of enterprise environments, a circuit-level gateway doesn't just pass traffic. It acts as a proxy. It functions as a definitive middleman.
Okay, how does that work in practice?
Well, when your laptop attempts to connect to a remote server, it isn't actually connecting to this server. It connects to the gateway.
So the pneumatic tube only goes from my car to the teller's desk.
Right. The gateway terminates your connection right there. It reads your request, turns around, and initiates a brand new secondary connection from itself to the destination server on your behalf. It relays the information back and forth between the two separate circuits.
Oh, wow. So the outside world never actually sees my real device.
Never. To the external server,
Yes.
all traffic appears to be coming solely from the gateway's IP address. The internal structure of your corporate network, the specific IP scheme of your laptops, your internal servers, the layout of your departments, that remains completely hidden.
That's huge.
It is. This abstraction improves the security posture immensely because external attackers cannot map out your internal network topology. They just see a single impenetrable wall acting as a proxy.
Okay, I hear the benefits. Speed, low latency, resource efficiency, and hiding the internal network map. But and there's a big, well, here, let's go back to the pneumatic tube analogy for a second, because there's a very obvious glaring flaw here.
I know where you're going with this.
If the system ensures the tube gets from point A to point B perfectly, but it outright refuses to read the letters inside the tube, how do you know an attacker isn't mailing a bomb?
Well, you don't. That is the pivotal, inescapable vulnerability of the circuit-level gateway. Zero content visibility.
And the documentation doesn't sugarcoat this at all. It states outright that despite the elegance of managing sessions, these gateways has catastrophic limitations in modern cybersecurity environments.
They really do. Because they can't see the content, sophisticated attacks slide right through completely undetected, as long as the attacker politely follows the rules of the session.
So if an attacker knows how to form a perfect TCP handshake,
And they're launching their attack from an IP address that hasn't been flagged or banned yet, the gateway rolls out the red carpet. The attacker establishes a completely valid, policy-compliant session.
wow.
Yeah, the gateway marks it as approved in the state table, opens the logical tunnel, and just steps aside to let the traffic flow.
And once that tunnel is open, the attacker can just start flooding it with malicious payloads.
The gateway is intentionally blind to the payload, so it cannot detect malware embedded inside the traffic. It will cheerfully forward a file containing a crippling ransomware variant because, to the gateway's logic, it's just authorized data flowing through an approved circuit.
That is terrifying. The sources list out some very specific unseen threats that breeze right past this type of firewall. Malware is the obvious one, like you said, but there are also SQL injection attacks.
Oh yeah, SQL injections are a classic example.
For you listening, a SQL injection is when an attacker goes to a seemingly normal web form on your site, like a login box or a search bar. And instead of typing their name, they type a malicious database command like delete all user tables.
And because that malicious text string is being sent over a standard web port through an approved TCP session, the circuit-level gateway sees absolutely no problem with it. It just waves the command through your internal database server, resulting in total data destruction or theft.
It also misses cross-site scripting, or XSS attacks, for the exact same reason, and it's completely blind to command and control payloads.
Yeah, the C2 traffic.
Right. Let's say a machine inside your network is already infected with a virus from an employee clicking a bad email link. That virus reaches out to a hacker's remote server to ask for instructions. The gateway just sees an internal machine initiating a normal outbound web request, validates a handshake, and allows the communication.
It's entirely oblivious to data exfiltration techniques as well. An insider threat or a compromised machine could be slowly draining terabytes of sensitive customer data out of your network, sending it to an external server. The gateway just logs it as a healthy, active, long-running data transfer session.
Look at that list of vulnerabilities, though. Malware, SQL injections, API attacks, data exfiltration. I'm looking at today's modern threat landscape, and basically every single major cyber attack making headlines targets exactly what this gateway ignores.
Yep, they go right for the payload.
Right. Attackers today aren't just trying to break network hardware. They're going after APIs, they're exploiting complex web applications, and they're hijacking user sessions. So in today's world, isn't this technology a dinosaur? Are we just studying an antique?
Well, as a standalone perimeter defense, a circuit-level gateway is entirely insufficient for today's threats. You just cannot rely on session validation alone when the contents of the sessions themselves have been weaponized. If a network engineer tried to protect a modern enterprise with only a layer 5 gateway, they'd be compromised in minutes.
So did we just throw this technology away then? Did the industry just toss the circuit-level gateway into the scrap heap of IT history and replace it entirely with layer 7 firewalls?
That's a crucial concept to grasp when you're studying the evolution of cybersecurity architecture. Fundamental technologies rarely disappear entirely. Instead, they get absorbed.
Absorbed, meaning the core logic was merged into something much bigger.
Exactly. Standalone circuit-level gateways like physical boxes where session validation is the only thing the hardware does, those are incredibly rare today. But the core functionality, that brilliant, highly efficient session validation logic, is very much alive. It was absorbed into the complex, multi-layered systems we rely on right now.
The documentation actually highlights a few specific places where this technology still serves as a foundational building block. It's heavily embedded inside proxy firewalls. It's a core component of modern VPN gateways, too.
Which makes total sense when you think about it.
Yeah, a virtual private network is all about establishing a secure, authenticated, stateful session tunnel over the public internet.
Exactly. It's also found deep within the processing pipelines of next-generation firewalls, often called NGFWs, as well as secure web gateways and various enterprise security appliances.
So it went from being the entire security system at the front door to being one specialized gear spinning inside a much larger, much smarter engine.
Think of it as an indispensable evolutionary bridge in firewall development. If we trace the lineage, phase 1 was basic packet filtering. Very rudimentary, very fast, but easily fooled because it had no memory of the conversation.
The postal worker just glancing at zip codes.
Right. Phase 2 was the circuit-level gateway. It added the stateful intelligence to understand and manage sessions without sacrificing that incredible speed. It was a massive leap forward in network abstraction and connection control.
And then phase 3.
Phase 3 brought deeper stateful inspection, and finally, Phase 4 is the modern era. Application firewalls and next-generation firewalls that perform full, heavy-duty content inspection integrated with real-time behavioral threat intelligence.
But here's the critical part. Those massive next-gen firewalls didn't just forget how to do phase 2. They didn't throw out the bouncer. They still used the circuit-level logic as an initial filtering mechanism, right?
Spot on. Why waste immense, expensive computing power having your Layer 7 customs agents open and inspect a package if the TCP handshake is completely broken to begin with?
That makes so much sense.
Yeah, you utilize the lightweight, blazing fast circuit validation to instantly drop the obvious junk traffic. If a connection fails the basic session rules, if it's malformed or coming from an unauthorized subnet, you terminate it immediately at Layer 5 before it ever reaches the heavy-duty inspection engines.
It acts as a highly efficient primary filter, preserving the firewall CPU and memory resources for the traffic that actually warrants a microscopic look.
Exactly. It's the ultimate layered approach.
The bouncer is still there at the front door, checking the VIP list and the handshake. If you fail, you are gone immediately, no resources wasted. If you pass, the bouncer lets you in. But now, just inside the door, there's a whole security team with metal detectors, X-ray machines, and behavioral analysts waiting to inspect everything you brought with you.
That is the foundation of modern defense-in-depth strategies. You combine the speed, efficiency, and network abstraction of the circuit gateway with the granular, content-aware security of the application firewall. They cover each other's inherent blind spots perfectly.
We have covered a lot of technical ground on this deep dive. Let's do a quick recap of the core takeaways from the architecture documentation. A circuit-level gateway is a Layer 5 firewall technology operating on a very specific premise. It validates network sessions and protects your internal network map with lightning speed.
Right. And it does this by rigorously enforcing the initiation, establishment, and termination of a connection, like the TCP handshake,
While intentionally ignoring the actual data payloads being transmitted.
which affords it phenomenal performance and exceptionally low latency, but leaves it entirely blind to content-based threats like malware, command and control traffic, or SQL injections. Today, it no longer stands alone at the perimeter, but serves as a vital session control and pre-filtering mechanism inside larger, multi-layered firewall architectures.
It's such a fascinating piece of the network puzzle. Just to realize that the systems keeping our data secure today are built on these distinct layers of logic interacting with each other.
It really is a marvel of engineering.
Definitely. Now, as we wrap up, there was one detail in the sources regarding the future of network traffic that sparked a really interesting thought. And I want you to unpack it for our listener before we go.
Oh, sure.
The documentation mentioned that modern cyber attacks heavily target encrypted traffic. We know that today, almost all web traffic is encrypted with protocols like TLS or SSL. When you see that little padlock in your browser, your data payload is encrypted.
Right, which presents a massive, escalating challenge for those advanced Layer 7 firewalls. To inspect the payload of an encrypted packet, the firewall basically has to act as an authorized man in the middle.
Okay, meaning what exactly?
It has to catch the packet, decrypt the data, analyze it for threats, and then re-encrypt it before sending it on to the destination. That decryption and re-encryption process is incredibly resource-heavy.
I can imagine.
Yeah, it introduces major latency, and it raises a myriad of privacy concerns, honestly.
So, here's the provocative thought to take with you today. As encryption algorithms become deeper and mathematically more complex, making deep packet inspection slower, more expensive, and sometimes even impossible due to privacy regulations, might the raw, lightweight, data-blind speed of the circuit-level gateway suddenly become critical again in the future of firewall design?
That's a huge question, because if we mathematically cannot afford to read the letters anymore, we are going to have to get exceptionally good at trusting the integrity of the pneumatic tubes.
A completely compelling architectural dilemma and a great reminder that foundational concepts in networking never truly become obsolete. They just wait for the right conditions to become vital once again. So next time you see a VIP bouncer at an exclusive club, give them a nod. They're doing Layer 5 session validation out there in the real world.
That's one way to look at it, yeah.